have a problem similar to counting a mixture of nuclides. I have considered N1 to 600, which means it's 60%, and N2 is 40%, and the N2, the second nuclide, is long-lived. The total data N of T, which is similar to the counts taken from a detector. We plot this data and we find a curve which seems to be exponential curve, but we have to explore it further. So we plot this data on the semi-log paper. On Microsoft Excel, I can change the axis. So set it to a logarithmic scale. Okay. And I see that the first few points over here, they seems to deviate significantly from the line, from a straight line. To see that more clearly, I will enhance this scale. So let me start it from 100. You see the effect. So the first few points seems to be quite away from an approximate straight line. So in this case, let's assume that there are two nuclides present in this sample, the hypothetical sample that has given us this data, and the equation prevails is this one: n of t equals n1 of 0 e to the minus lambda 1 t plus n2 of 0 e to the minus lambda 2 t. So I plot the final part, final data, say after 45. So final part again on the same paper, and for the time being I can show it. I can just activate that data. So I show the last part and apply, and this part turn out to be a straight line, final part. And if I extract the model from this final part, in which only the contribution of one nuclide is present, so it turned out to be 600 e to the minus 0.035, 0.035, thanks to Microsoft Excel and the built-in regression model. So with this data, the intercept value so I say, okay, this is n1 of t. So we found that it is equal to 600 times on a graph paper. We can do the extension like insert okay. So if I extend this line, not this one, let's Well, it's very difficult how to find the proper controls. Okay, yeah, this line. Okay, so I will extend this line, this red line, honestly, and to show it right. It has rightfully covered the red line, the contribution of the long-lived isotope. And we extended that to the initial point, and from the intercept you can find, if I uh, change the scale, if I read from 100 as the starting point, so this line that has manually been drawn, this will be changed. So the point somewhere here is up to 600. Then I show the grid lines. Okay, minor grid lines. So this seems to be, well, 200, 300, 400, 500, 600, and 700, right? But this has been shifted. Let me again. So somewhere 600, right? So I agree with the regression line. I agree with the regression line. Let's put it back. Okay. So 600 as the intercept. So now we have the model for the long-lived isotope. So I can say now the data is 600 times e raised to the power minus 0.035 times t. So this will become 600. And this is going to prevail for the most of the data. You can see in the final part, the values are almost equal, right? Now to see the short-lived isotope, we have the contribution from N1 in of T. So I will do the calculation for N2 of T, which is basically the calculating the difference between the total activity and the activity contribution from N1. And mathematically, okay, it is possible. So you will do calculation N of T minus N1 of T. And then this column will become the problem of one single isotope problem, right? Now N2 of T, when plotted with against the time axis, it will be the single nuclide. So from the two nuclide problem, you can do this decomposition of the radioactivity contributions. So I will add another series to it. The time axis. So first 50 time units in minutes, okay? And here. So these are these yellow points. I hope they are visible. And now this is just one nuclide. I asked Microsoft Excel to help me adding the trend line. And this line is a straight line on a semi-log paper, which means there is an exponential relationship. And I also request Microsoft Excel to give me the equation, and that's it. The line there is a straight line, okay, and the equation is 200 e to the power minus 0.11. Let's help it shine. Okay, so 200 e to the power minus 0.11 x. So in my theoretical problem, it was 0.017. So due to numerical trade-offs, numerical errors, the values are slightly different. So two nuclides problem. You have to first see the long-lived isotope in the later part of the data, and then you subtract the long-lived contribution in the earlier part of the data. So with this demonstration, I do hope that the extension of this is really logical.